Yeah, building as power plant, and why I not have in the contents of energy zero, because I'm an engineer and teaching architects, and as an engineer I know what zero means, and I don't know how to reach a zero energy building, because zero is something, and the end of the year maybe you say zero. I don't know how we reach that. Maybe it's negative or positive, our balance. So this is the reason we in Germany we don't speak about zero energy. Zero emission, as you're speaking, are perfect, but zero energy, I don't understand what this means. Nobody could told me that in the past. So let's go ahead because my time is short. And smart building in smart grids in Germany, we are, let's say, starting in the 70s. It's my age. This, on the left side is my first project. This project here in Aachen. It was the first project where we're trying that the building is self-sufficient. And this was the time when we starting with the first collectors, with the first storages, big storage and big house. We built a big storage and built a house around. This was in the 70s. And then, let's say, comes the people who's thinking on passive solar. Say, okay, forget all these active systems. We put a lot of window garden, a lot of glazings, and this is the best solution we can have, passive solar. We from the active side, okay, we said maybe it's a solution or it's an option. Later on, we starting in our group with thinking more big. Big is big thinking, because we learned that a single house with a big storage is maybe not the only option. So we're thinking on called district heating. So our friends from Sweden, I worked a lot in the IEA, we're thinking on huge solar district heating system with huge big storages underground, thousands of cubic meter of solar, of water or ground gravel or whatever. And this was the 90s where I worked more in this field of large systems. And big storages, we learned a lot about how to build a storage, concrete storage, water vapor tight, not watertight. Watertight is simple, but water vapor tight is more challenge. And then comes the, let's say, transparent insulation people, and later on, also as I told you, the more passive, this was more passive solar. It's much different as what we now, what very fashion in Germany is a passive house, whatever this means. I will tell you that I'm against this technology because I don't like to have 30 centimeter insulation and 40 in the roof and only triple glazing and very tight and all these things. So I'm not in favor of passive houses, but in the German definition of looking only on the heating part of a building. And then comes the time where PV makes the goal or makes the let's say win the competition in Germany, we can say that, because the PV have drops down factor of 10 in the system cost. It drops down a factor of 10 in 5 years period, drops down the system cost of factor of 10 for the PV system. And this time coming, the solar assemble people have a lot of problems. And this was the time when I changed a little bit my mind, what is the future? And I think the future is electricity. And electricity based on renewable is the best solution you can have on building context to using PV systems. And this was the time, let's say 5-6 years ago, where we started this approach on called active houses. A little bit again, this passive house people thinking, we're thinking only like in heating, and we're thinking in, let's say, the whole energy consumption for the building, including the mobility. So also including all appliances, all energy you need, and you will see in our measurements that in the most of the new houses, the heating and the hot water is a minor demand of the year, maybe 30-40%, and 60% is the electricity you need for your household, for all your, let's say, digital equipment and communication and whatever. So this was, let's say, a short story of my life, let's say, 40 years in solar and 40 years in energy efficient cities and buildings. And actually we're working more, I have to say, open on districts as on single buildings. But this is a little bit what I show you today is the last 5 to 8 years. This is the, let's say, the approach in Germany. What we have grids, we have central power stations, and the future should be more. This is the German policy since 2010. Decentralize the energy production of more decentralized instead of centralized. Maybe you know that we decided to switch off all our nuclear power stations. We switched off 8, nothing was happened, and we have still 10, and also this will switch off 2022. So this more decentralized energy supply of our country is, of course, then also a potential for decentralized solar thermal or solar energy is a decentralized energy. We know that since many, many years. So this is a good basis in the large scale, not in the single building scale. So my message is passive house was yesterday, active house is the future. And the reason I say that is due to that the energy is now come so cheap, very cheap from PV. Give you an idea. In Germany, the PV full cost from the house, from the roof, from a larger system, let's say from a school, is one third of the energy grid price of electricity. 1/3. This means the electricity from the roof is 30% cost of the full cost from the grid. Compare maybe to Norway, we have higher electricity price. We have 30 cents per kilowatt hour from the grid. And we're producing from the roof, full cost, when you go by the bank, loan and so on, by 10 cents. We buy it by 30 cents and we can produce it by 10 cents. So this means we are fully economically. And the only challenge is to use the electricity in the house. But we could not do it in the whole year, but we have to interact with the grid. And this is, we call it the smart grid. So from an engineering point of view and architecture point of view, we have to go to optimizing between reduction, but the question is how much reducing the energy consumption, and producing from renewable sources. This is the challenge of engineers and architects. And our definition on this, let's say, plus energy building active house is on the yearly basis, not in every second, not in every minute, is we have this plus balance. And we call that, you can read that, from energy consumption to an energy to a generating building. And the second approach is on the life cycle. We say that the energy payback time is shorter than the lifetime. Means you see that better maybe in this diagram. Maybe I show you this one. This is on the lifetime. On the lifetime, at the beginning when the house is built, we have an offset. This is all the embedded energy you need to build a house. All energy was included mainly in the, let's say, in the massive part of the building. In Germany, maybe you know that we're building with stones and concrete and cement and things like that. And so the most of the energy, the embedded gray energy, is not in the equipment. It's in the glass and in the concrete, in the massive construction of the building. So this is when you're starting the building or you renovate the building, you have a certain energy need to build the building or to renovate the building. And the surplus energy building over the years, it's producing more as it's consumed, and to a certain time, maybe here 20 years, you're producing more surplus as you need in this time. And this is, from my point of view, this is a real approach. That during a certain lifetime, you have an energy payback during your lifetime. Come back to the yearly balance. The yearly balance, we have a German standard called ENEF. And in this German standard, the cooling load and the electricity for lighting and all appliances are not included in our whole approach. This is actually the actual standard in Germany. But the active house or the energy plus means everything is included. You see here the appliances, here washing machine, computers, everything is included in our balance. This is the building balance over the year, the cooling load of the house as well as the lighting. And of course the traditional hot water heating. This is auxiliary and ventilation. So when you look on a certain picture, this is what I mentioned before. This is an actual yearly balance of a multi-family house. here the demand, and here the PV gain from the roof and the facade. This is the roof, and these are the facades, because this is a 5-story building, we'll show you later on. And if you're coming higher and higher in your building, you have more and more challenge to use only the roof to cover your whole demand, because the roof not increasing, but the floor heating increasing by higher buildings. So single-family houses, no problem, also no problem in Norway. But if you go in real projects in cities, in multi-family houses, then you have the challenge to use the facade in addition to the roof. So you see in this picture, this is the heating, the hot water, the accelerator is the ventilation, and you see the space heating and domestic hot water. In this, it's a new building, I have to say. It's 30% of the whole consumption. And this is the end energy of this building. And most of the consumption is the appliances in this house. But there is not appliances like, let's say, very old appliances. That's very normal, new appliances, washing machines, fridge, everything what the modern household have in use. So because my time is short, I would like to make a little bit advertisement. I have written 2 years ago in German, this book Energy Plus, and all the projects we have designed and we have done and monitored is written in this book Energy Plus. It's published 2013 in English, and now it's in Chinese. So if you're interested, I have not a version with me. Normally I have a version with me. I not expected so much audience, but it's available, and I think there is a lot for engineers and architects written down. Give you some projects. You have seen in this introduction, when you speak about things, my opinion is to have to do it and to have to experience by your own with it. This is maybe the reason that in German university professors in our faculty of architecture, all of us who are architects and engineers have a more or less bigger company beside the institutes, because we all full with both legs in the practice. So this is the reason that we only maybe 3 days on the university and the rest of the week we in our companies. Otherwise, I don't how to teach our students how to build buildings and how to build cities when I not really do it. And this is the reason I built one for us private. Some years ago, 5-6 years ago, was the design. And this house is in an existing area. It's not on the green outside of the city. And I would not like to explain you the architecture. I would like to show you some pictures of the house itself and some features. What is the features of the energy design? Of course, we from the active side, we're not against insulation and not against good windows and not a good envelope, because I'm always teaching in building physics and building services, envelope. So an excellent building envelope is basics and openable windows for me must. Yesterday I come here in this excellent nice city in the hotel, and there was no window in my room, and of course I changed it. I changed the room, because I could not sleep in a room without an openable window. And openable windows for me must heat recovery of the ventilation, PV and heat pump. I'm sorry to say that, because I'm coming from the thermal side, but I see the only future, not the only, but one of the advanced system for the future is a heat pump combined with a PV system, heat pump or cooling machine, because it's so simple to cool down buildings in Cairo or in Bangkok or in I don't know where, because most of the people living on the other side of the climate means they need dehumidification and cooling. And so there is a perfect, we know that from our project, with PV and cooling machines. With PV and cooling machines, with compression cooling machines, you can perfect cool down buildings. And this means PV and heat pump is for me the system for the future. And low temperature radiation, floor heating, or ceiling cooling in office buildings, concept for energy storage, a big challenge. So we'll say something to that later on. And demand side management is the features, let's say, especially from the engineering side. Give you here an example. Most of the people say this PV have less efficiency. This is right. From 100% solar, you only get 15% electricity. But with this 15% electricity and a good heat pump, you make 60% energy. Because the heat pump has a CO2 of 4. This means 4 multiplied by 15% is 60. So this means, finally, the energy that comes out of this system is 60%, and the solar thermal system have to fight for 60% over the year. And so this means there is, for me, not only one solution. There is a solution of solar thermal. We make a lot of investigation also on private houses. But as an engineer, I could tell you I can very well sleep with a PV. Nothing will be corrosion, nothing will be frozen, nothing will be turned. Sometimes you get gray hair when you're working on solar thermal. I can tell you that. It's hard to work on it. But I hope that this society will survive, or this group will survive. Mobility. Also, the building and the mobility in the city will come more and closer together. And this is the reason that also in Germany we have a huge program on e-mobility. I starting with this house on a smart. Now we have an BMW E3. This is of course more advanced e-mobility. It makes really fun to go with this car. 150 kilometers the distance. What you can drive with one full battery, and it's really a sportive car. And it makes fun to drive with it. And it's loaded by the PV from the roof. Here gives for the architect some impression that is my architecture I like more purism architecture. Maybe we can copy the Bauhaus in this sense. So I like this. And you see it, on some people ask me, oh, you have such huge window on the south, you will cooked in the summer. Nothing happened. We have a good shading outside, and the house is massive. There is no overheating, no problem with overheating in summer. And this is the concept, and maybe I would not like to boring you with the concept, but there's a lot of measurements, a lot of counters to evaluate the whole building. I will show you the results soon. And the basic energy source is the ground. It's a ground-coupled heat pump. And the ground-coupled heat pump is fed by the PV systems mainly. Also, by the way, in winter. When in winter, no sun, really, there is only light, means daytime. This 15 kilowatt peak on the roof produces nearly 2 kilowatt peak when it's totally overcast. Totally overcast. Sometimes when it's raining, small raining, we still have 1.5 to 2 kilowatt peak. And with 2 kilowatt peak with the heat pump, you can make 8 kilowatt peak heat. And with 8 kilowatt peak heat, I can heat a house completely. So this is, we have to think about, not only on components, only on system approaches. So let's say I would not like to go really in the technical design. This is let's say the heart. The heart of the building is this heat pump. This is the air system, the heat recovery system. And this heat pump have a power of 2.5 kilowatt peak and an output of nearly 10 kilowatt peak heat. And this is the batteries who are in the house. This is an 8 kilowatt hour lead battery, and this is a 20 kilowatt hour lithium ion battery. And these batteries are used, of course, to increase the self-use energy from the PV in the house. This is what I told you, to increase, to not only feed in the grid, to use the electricity in the house. This is the challenge what we have for the future. This is the new BMW. I'm very happy about this car. The monitoring result, the first 3 years. The first thing is that this house, I have to say that the generator on the roof is designed as big the roof is. So simple is it. The PV could be smaller to get the surplus. You see that here. We have nearly 80% more electricity produced as we need for everything. So this means we could reduce it. But we use the roof as it is. And you see that this is the balance. This is what we direct using. And this is what we're supplying to the grid. And so this means in 2012, the first, it was the second year, we have nearly 30% using the electricity direct in the house. Now, after certain years, we have increased that by more optimization up to 40%. And you see the coverage, when you say the solar coverage is 50%, it means that solar fraction or solar coverage is 50%. And this you see, this is not an autonomous or a self-sufficient building. You need the grid, and you have to supply your neighbors in the grid, in the smart grid. Some neighbors have no PV, some neighbors have PV. So this is a kind of an interaction between the society. Here you see over the years, this is the production of the PV on the roof. Here you always see in summer, okay, it increases very quick. Then in winter we have, of course, a smaller increase. And so after this, now after this 3.5 years, we have 16,000 kilowatt hour surplus. What is 16,000 kilowatt hours? You can say normally a family with 4 persons can need 4,000 kilowatt hour for the electricity in normal households. So this is 4 years for 4 years consumption for a normal family this is the energy what is direct used, and this is the energy who is put in the grid. Yeah, there is a lot of measurements. Here, this shows you the result. This is heating and hot water of the house, and this is the household or the appliances and the mobility. MSR means the measurement, all the equipment for measurement, because it's a research project. But here on this figure, you see the heating and hot water is 1/3, and 2/3 have nothing to do with heating and hot water. What means we have to put attention on the whole energy consumption, not only on heating and hot water. And here some figures. This is the circulation pumps, the measurement system, the air ventilation system, the household appliances, the lighting, and others, and this is the total, and so on. So there's a lot of detailed measurements, and this is the reason that we have nearly the same electricity consumption for the measurements as for the household appliances. For cooking and cooling, we have the same electricity. This means also, very interesting result, also we had for office buildings, that building management system, building automation, is not energy-free. Do you think that is energy-free? When you measure building management systems, building automation, you will get idea how much energy 8,650 hours, they sucking electricity from your house. So be careful if you put too much automation in buildings. It's an energy. Now the energy is off here. Aha. This house is not only an energy surplus; it's also a money plus. And money plus means we have in Germany this rule that you get money when you put in the grid. I don't know how it's in Norway. But in Germany, it's funny that this building was put in operation 2010. We had a very good feed-in tariff policy. In this time, now it's over. But it's happened 20 years. When you build it, this will be valid 20 years. And you see, this building have now made an earn 18,000 euro. 18,000 euro, maybe is this 150,000 Swedish crowns? I think I have to multiply this by 8, something like that. So in this time of the first 3 years, the building earned 150,000 Norway crowns. I said Swedish crowns. No, Norway crowns. Okay, so this was the first project, and then I think I have to look what's the time left so that I... Huh? Okay, I have to speed up. This is because after the single houses we are designed, we said single houses is not the future. Single house, multi-family houses is the future in Germany. And multi-family houses in the city. And so we're starting with these houses in the city. As I told you what the challenges is, the higher you build, desto less roof you have. This is the reason we have to go in the facade, and in the facade, what we have to learn, maybe more in the future in the facade, how to make cheap integration in the facade. Because actually in Germany, when you compare the system cost on the roof to the facade, we have a factor 1 to nearly 2.5. So 1 kilowatt peak in the facade costs us 2.5 more as in the roof. So this we have to work on it. But we need we need the facade to get this plus energy balance. Okay, there is a lot similar as with the single house. We have PV. We have PV in the facade. We have a much bigger battery, lithium iron phosphate battery, and we have also in this case an ice storage. The reason is that we have an ice storage here because the clients would have to be an ice storage. I'm not in favor of it. But the heat source, in this case for the heat pump, is the ice storage and, let's say, a heat exchanger on the roof. The building is now nearly finished. This was a picture some months ago. This is the inside of this ice storage, 100 cubic meter. The next project is a much bigger building with 72 dwellings. A big challenge for the architect. My friend Manfred Hegger, where I have worked with him together on Solar Decathlon. We win 2 times in Washington, D.C., the Solar Decathlon, 2007 and 2009. And so our friendship is continued in such real projects. And this other project was also in Frankfurt. This project is also in the Frankfurt city. And we had only this plot, a very small plot of 9 meters. And this was the challenge to build there a multi-family houses of 9 meter plot. And so this was the solution. And also we have to use the facade. Here we had the luck that we could using the sewage channel for the heat source. So this sewage channel, we put in some stainless steel heat exchangers. And we're using this during the heating and during the summer season, the temperature in the sewage system for the heat pump and heat and producing hot water by PV over the heat pump for this multi-family house. There's a lot of things also we're doing beside the engineering and architecture part, this interface between the humans, how the humans interact of these houses as the indoor environment, as the energy, as the electrical mobility. So we had a team of social pedagogue and of psychological people in the team, and so we developed certain interfaces on apps how they could interact. The most thing, of course, we're doing that they show that how much euro, how much money, how much dollar you have used, and what have the other used, and this is more a challenge between the people in such dwellings. I skipped that because I have no time. Or this is the commercial buildings. Then this is one of a nice building. Also, I like we do the engineering, and Manfred Hegger do the architecture design. It's an education center for SMA. SMA is the world market leader for inverters. The device who convert DC in AC electricity. And also we learned a lot on this project, a lot of measurements, a lot of monitoring, a lot of how to integrate PV in the facade. And finally, maybe I should, because I had yesterday a nice talk with Frederick, Dean in Trondheim. I think we're now working on, okay, now it's finished from my time, yeah, okay. I see. I'm finished. Wait, I'm finished. I will only switch it off. since 2-3 years, my favor is in districts. And because I see that the challenge is in districts. And one of the districts we now doing close to Stuttgart is called Esslingen. Esslingen, they have a new area. It was a previous railway area. And now 5,000 dwellings will be built in this area. And for this district, city district, we developed this type, what I show you for the multifamily houses. Let's say a smart grid with all these things, what we call it power to gas, producing hydrogen, and feed in the gas grid. And power to heat means we're using PV via the heat pump and put it in big storages, like what we have done many years ago with solar thermal, and using this power to heat for shifting from summer in the winter time. So this will be in a huge scale, also e-mobility. We have Bosch, Mercedes in the team. And I think the future... Also yesterday I speak with Annegret Hesters from Trondheim. Maybe we are in a similar age. And normally I said to myself, I have to stop to a certain time in my age to enjoy more the life. But when you work on such future projects, it's very hard to stop. Thank you.